Hello, welcome to this tutorial on beam buckling. The idea is to guide you through a very simple example and to show you how you could find the ideal stiffness for a simple beam. Let's click on features. This will tell us all the features that we have now in our model, which is not a new model. I have already run this model to make it faster here. But let's see what we have. We have pin and roller supports, springs, point loads, stiffeners, and we are doing an erection analysis and also an eigenvalue buckling analysis. See that you can define other types of boundary conditions, bracing and analysis, or loading. Let's click on next. The beam here is 60 feet long. The material properties are very standard for steel. I have two supports, a pin at one end and a roller at the other end. So for pin, it's 1, and for roller, it's 0. I have two stiffeners, actually at just one location. That's why I have one here at midspan, so at 30 feet. Side 3 means that it's on both sides of the web. Its thickness is 0.5 inch and its width is 5.2. So that really applies for the two stiffeners which are on both ends here at 30 feet. I have one spring, again at 30 feet, and then I have it on that node here, node number 8, and it's a lateral spring, so it's acting in the x direction for a straight girder, so x here, so 1, 8, and 1. And the magnitude of that stiffness is 0.71, which is just under the ideal stiffness. I don't need to store the reference points because I have already run this model. If this is a new model, of course, and you get to this form for the first time, you need to click on this. You also need to click on this if ever you change any of the reference points here, which are supports, splices, stiffeners, cross frames, etc. This is all summarized in this text if you have the time to read it, but we don't need to deal with that here because the model is already set up. So we can just hit next. We have 4 elements through the web depth. We could have 8 if we wanted to, but here it's okay to have 4. The mesh size for each segment is 18, and you see here I have 2 segments because I have defined really 3 reference points: the ends of the beam at 0 and 60, and the stiffener and the spring at 30. So that gives me 2 segments or 3 reference points. 18 inches for both of them. These are the cross-sectional dimensions, which are given here: flange width and thickness, web depth and thickness. It's a uniform beam, so I'm assigning profile number 1 to the 2 segments. And I have just one stage here. I'm not defining a full erection sequence. I have just one stage, and for girder 1 I'm turning on the full length, so between 0 and 60 feet. I can apply a stiffness modifier on the spring. I can deactivate it if I wanted to. That's in case you have maybe temporary supports. That's a nice way to model temporary supports. You can just hit next here. I have 4 point loads which are applied at 2 and 8. So nodes 2 and 8 are the top flange node and the bottom flange node, and the loads are acting in the longitudinal direction, so that's direction Y or 2 here. I'm applying only unit loads. Okay, the idea is to have a uniform moment along the bridge. I'm not turning on the self weight here because I just want uniform moment along the bridge, so C sub B equals 1. And I'm running an eigenvalue buckling analysis, so 1 here. in this cell. And I can just click on Run. Let's extend this. Let's zoom in. We can see the spring. And by clicking on this checkbox here, we can see really the flanges and the stiffener here. And point loads and supports. So the idea is to have a uniform moment along the bridge. Color code is given here on this button. This is a nice way to check the model and cross-sectional profile assignments. This is the linear elastic solution. Tiny displacements, of course, because I'm applying only unit loads here. So really a moment which is equal to 1 times the web depth. So about 30 kip inch. So it's really small. So of course it won't deflect much. But what's really interesting is to check the buckling mode. Let's scale this down. Let's see what the beam does. It is buckling here between the ends. So the spring that we have here is not stiff enough to brace the beam. So 0.71 kip per inch is under the ideal stiffness. It's less than the ideal stiffness. Now, if we close this form, we go back to the springs form and we change this to 0.72, which is slightly higher, just barely higher. And we don't need to store the reference points again because the spring has not changed location. It's still at 30 feet. So we don't need to go through the forms that we've seen before. We can just go back here, hit Run. We can see that hopefully now, let's see, the buckling mode, the first buckling mode is actually a mode where the top flange buckles between the brace points. So 0.72 is just above the ideal stiffness. So this is it. This concludes this simple example on beam buckling and ideal stiffness. Thank you.